Everyone is watching the wrong metal. For the last several years, global markets have been locked into a familiar obsession. Lithium shortages, copper supercycles, cobalt constraints. Analysts built entire investment theses around the electrification narrative, assuming the future of transportation would be defined by batteries alone. The logic seemed airtight. Electric vehicles need batteries. Batteries need lithium. Cars need wiring. Wiring is made of copper. Therefore, buy lithium. Buy copper. Buy the materials of electrification. Capital flowed exactly where the story pointed. But markets have a weakness. They follow stories, not systems. And while investors were busy modeling supply curves and demand forecasts, something far more important was happening inside engineering labs, not trading floors. The future of the automobile was being quietly redesigned, not at the battery level, but at the electrical nervous system level. Because the problem was never energy storage. The problem was distribution. For more than a century, vehicles have relied on a 12-volt electrical architecture. It was a standard born in an era of simplicity, when cars needed only enough electricity to power ignition systems, headlights, and basic accessories. Radios were a luxury, sensors were non-existent, software didn't exist. The 12-volt system survived because it worked. It was cheap, it was familiar, and it was good enough, until it wasn't. Modern vehicles are no longer mechanical machines with electrical add-ons. They are electrical platforms with mechanical components attached. Cameras, radar, onboard computers, electric steering, brake-by-wire systems, advanced climate control, infotainment, connectivity modules. All of it draws power, constantly, simultaneously. The load has exploded. Automakers tried to compensate the old way. More copper, thicker wires, heavier harnesses, more complex routing. Entire vehicles began carrying kilometers of copper wiring, adding weight, cost, and inefficiency. Every additional kilogram reduced range. Every additional connection introduced resistance, heat, and failure risk. Tesla saw this coming years ago, not as a cost issue, as a physics problem. Copper is an excellent conductor, but it is heavy. It scales poorly. And in a world where electrical demand grows exponentially, copper-based systems reach a point of diminishing returns very quickly. Tesla engineers understood something Wall Street didn't. You don't fix an electrical bottleneck by adding more metal. You fix it by changing the architecture. That realization led to a decision that quietly rewrote automotive engineering rules. With the launch of the Cybertruck, Tesla eliminated the traditional 12-volt electrical system entirely and replaced it with a 48-volt architecture. No marketing campaign, no dramatic reveal, just a technical footnote buried in engineering discussions. The media called it a cost-saving measure. They weren't wrong, but they weren't right either. At higher voltage, the same amount of power can be delivered with less current. Less current means thinner wires. Thinner wires mean less copper, less weight, higher efficiency. On paper, it looked like a simple optimization, but physics always collects its debt. When voltage increases, electrical behavior changes. At 48 volts, electricity becomes aggressive. When a circuit opens or closes, electrons don't politely stop flowing. They jump. This phenomenon is called arcing. An electrical arc is a miniature lightning bolt, a concentrated burst of energy that generates extreme heat in a fraction of a second. It erodes metal. It melts contacts. It welds components together. In low voltage systems, arcing is manageable. In higher voltage systems, it becomes destructive. This is where copper fails. Copper contacts exposed to repeated arcing degrade rapidly. Brass fares no better. The metal pits, oxidizes, and eventually fuses, shut. Switches fail. Relays die. Entire systems become unreliable. There is only one metal that consistently survives this environment: silver. Silver is not just a good conductor, it is the best conductor of electricity on the periodic table. More importantly, it disperses heat efficiently and resists surface degradation under arcing conditions. In high reliability electrical systems, aerospace, military hardware, industrial automation, silver-based contacts are not optional. They are mandatory. Tesla didn't discover this. Electrical engineers have known it for decades. But Tesla was the first automaker to scale this reality into mass-market vehicles. At 48 volts, every critical switching point becomes a silver decision. Relays, contactors, power distribution nodes. Where copper once worked, silver now becomes essential. And this is the moment the story shifts. Because Tesla's move wasn't isolated, automotive engineering does not exist in silos. Suppliers serve multiple manufacturers. Standards propagate across platforms. When one company proves an architecture works, others adopt it. Ford followed, General Motors followed, Toyota followed. Not because Tesla did it, but because physics demands it. Software-defined vehicles require stable, high-capacity electrical systems. Autonomous driving systems require redundancy and absolute reliability. Safety regulators demand fail-safe designs. The 12-volt system cannot survive this future. The transition to 48 volts is no longer a Tesla experiment. It is an industry inevitability. and that inevitability has consequences. Copper demand per vehicle may decline, but silver demand does not. It rises, quietly, systematically, across millions of units. This is the part the market completely missed. Silver is not treated like an industrial bottleneck. It trades like a monetary curiosity, volatile, speculative, ignored. But unlike lithium, silver is consumed. It doesn't get recycled efficiently. It doesn't sit idle in warehouses. It disappears into products, scattered across global infrastructure. And global silver supply is fragile. Most silver is produced as a byproduct of other mining operations. There are very few primary silver mines. When demand rises, supply cannot respond quickly. Now layer on solar energy, grid modernization, defense electronics, medical technology, each competing for the same metal. Tesla didn't just redesign a vehicle, they exposed a structural weakness in the global material system, a weakness hiding in plain sight. To understand why this matters, you have to stop thinking about silver as a commodity and start thinking about it as a system constraint. Silver is not rare in the way gold is rare. It exists in the Earth's crust in meaningful quantities. The problem is not geological scarcity. The problem is accessibility. Unlike copper or iron, silver is almost never mined for its own sake. The majority of global silver supply is produced as a byproduct of copper, lead, zinc, and gold mining. That means silver supply does not respond directly to silver demand. If copper prices fall, silver supply falls with it. If base metal mines shut down, silver disappears. If new silver demand emerges, production cannot ramp quickly. This creates a delayed, brittle supply chain. For decades, this fragility didn't matter. Silver demand grew slowly and predictably. Photography declined. Jewelry fluctuated. Industrial usage expanded gradually. Then electrification arrived. Solar panels quietly became one of the largest single sources of silver demand on Earth. Each panel uses silver paste for electrical contacts. Millions of panels became billions. Demand surged. Yet even that did not break the system. What Tesla's 48-volt shift introduces is something different. Not incremental demand, structural demand. Once an electrical architecture crosses a voltage threshold, material requirements change permanently. There is no downgrade path. There is no alternative metal waiting in the wings. At higher voltages, reliability stops being a preference and becomes a mandate, and silver sits at the center of that mandate. Every relay designed for a 48-volt environment must be rated for arcing resistance. Every contactor must handle repeated switching without welding. Every safety-critical circuit must survive worst-case scenarios. This is not an engineering debate. It is settled science, which means suppliers must redesign components. Tier 1 automotive suppliers do not design parts for one model. They design platforms. Those platforms get reused across dozens of vehicles, across brands, across continents. Once a supplier commits to silver-based contacts, that material choice propagates across the entire ecosystem. This is how silent demand builds. No headlines, no press releases, just purchase orders. The automotive industry produces roughly 90 million vehicles per year globally. Even modest increases in per-vehicle silver usage translate into enormous absolute demand, and those increases are not modest. A modern 48-volt vehicle contains dozens of switching elements operating at higher stress levels than their 12-volt predecessors. Even if each component uses fractions of an ounce, the aggregate adds up quickly. Now multiply that by millions of vehicles. Then consider the second-order effects. 48-volt systems do not exist in isolation. They require new tooling, new testing standards, new safety certifications. All of those systems rely on the same material properties, silver demand compounds. At the same time, silver inventories are already thin. Above-ground silver stocks are not like oil reserves. They are fragmented, hidden in private vaults, locked inside ETFs, embedded in electronics. There is no central authority tracking how much silver is truly available for industrial use. What is known is that annual mine production barely covers current demand. Any sustained increase creates a deficit, and deficits do not resolve themselves quietly. They resolve through price. But price is not the first signal. Availability is. Manufacturers notice shortages before markets do. Lead times extend. Premiums appear. Long-term contracts replace spot purchases. By the time investors notice, the physical metal has already moved. This is why silver demand shocks historically appear sudden and violent. They are invisible until they are unavoidable. Tesla's move accelerates this timeline, and it does so at the same moment global infrastructure is undergoing its largest electrical transformation since the Industrial Revolution. Power grids are being upgraded, data centers are expanding, defense systems are modernizing, medical equipment is becoming more electrically intensive. Each of these sectors already competes for silver. Now add automotive electrification at scale. This is not a story about one company. It is a story about convergence, multiple megatrends colliding on a single material, and silver does not scale. Unlike lithium, there is no flood of new projects waiting to come online. Unlike copper, There are no massive new deposits being developed specifically to meet demand. Silver remains trapped inside other mining economics, which means demand growth translates directly into stress. This is where the narrative breaks from Wall Street assumptions. Analysts model demand as if supply will respond. It won't, not in time, not at scale, not without price dislocation. This is why Tesla's decision matters far beyond automotive margins or vehicle design. It exposes a blind spot. Markets are focused on energy storage. The real constraint is energy control. Switching, distribution, reliability. These are the unglamorous systems that determine whether electrification actually works. And those systems depend on silver, not because it is precious, because it is necessary. The irony is that silver has always been hiding in plain sight. Every electrical engineer knows its value. Every high reliability system depends on it. But markets treat it like a monetary relic. The disconnect cannot last forever. Once physical shortages appear, narratives change quickly. Silver stops being an afterthought and starts being a strategic input. And strategic inputs attract attention. Governments notice. Manufacturers secure supply. Speculators arrive late. This is the pattern. Tesla didn't trigger this with a press release. They triggered it by redesigning reality. The reason markets keep misunderstanding silver is simple. They keep asking the wrong question. They ask how much silver exists in the ground. They ask how much silver was mined last year. They ask how many ounces sit inside vaults. Those questions sound logical, but they completely miss the point. The real question is not how much silver exists. The real question is how much silver is available at the exact moment modern systems need it. Availability is not geology. Availability is logistics, incentives, and timing, and silver fails all three. Most people assume that if demand rises, miners will simply produce more. That assumption works for metals that are mined intentionally. Iron ore responds. Copper eventually responds. Lithium responds aggressively because entire companies exist solely to extract it. Silver does not work that way. More than 70% of global silver production is a byproduct. It comes out of the ground only when other metals are profitable enough to justify mining. Silver production is hostage to copper prices, zinc demand, and gold economics. This means silver supply is not elastic. It does not stretch when pulled. When new demand arrives, silver does not surge toward it. Instead, the system tightens. Inventories thin, premiums rise, contracts get longer. Smaller buyers get pushed out. And this tightening always begins invisibly. Manufacturers notice it first. An automotive supplier redesigning a relay for a 48-volt system does not go to the spot market and buy silver bars. They sign long-term contracts with refiners. Those refiners, in turn, secure material from miners and recyclers. Each layer adds friction. Now multiply this process across dozens of suppliers, hundreds of components, and millions of vehicles. The result is not a sudden spike. It is a slow disappearance. This is how industrial shortages form, and it is already happening. Solar manufacturers learned this lesson first. As solar adoption accelerated, silver paste became a bottleneck. Engineers tried to reduce silver content per panel, but efficiency losses imposed hard limits. Silver usage per panel declined, but total demand kept rising because volume exploded. Electric vehicles follow the same pattern. Engineers can optimize, but they cannot eliminate silver without sacrificing reliability. At higher voltages, failure modes are unforgiving. There's no tolerance for cheap materials. A single welded contact can disable an entire system. A single degraded relay can cascade into system-wide failure. This is unacceptable in consumer vehicles. It is catastrophic in autonomous systems. As vehicles transition from driver-controlled machines to software-controlled platforms, electrical reliability becomes a safety issue, not just a cost issue. And safety has no substitute. This is why regulators matter. When regulators update standards to reflect higher electrical loads and autonomous requirements, they implicitly lock in material choices. Once a standard specifies performance thresholds, manufacturers must meet them regardless of cost. Silver clears those thresholds. Copper does not. This is where the transition becomes irreversible. Once standards adapt, reverting to older architectures becomes illegal, not just inefficient. Tesla's decision accelerated this regulatory timeline. Not because regulators follow Tesla, but because Tesla demonstrated feasibility at scale. When a technology works in the real world, regulators gain confidence to update rules. This feedback loop is powerful. Innovation proves possibility, standards enforce necessity, and necessity drives demand. Now consider the geopolitical dimension. Silver is not evenly distributed globally. Major producing regions include Mexico, Peru, China, and a handful of other countries. Political instability, environmental regulations, and resource nationalism all affect output. At the same time, the largest consumers of advanced electrical systems are industrialized economies with limited domestic silver production. This creates strategic dependence. Energy infrastructure, transportation systems, defense hardware, and medical devices all rely on a metal largely sourced elsewhere. That is not a comfortable position for governments. History shows what happens next. Governments begin classifying materials as critical. Strategic stockpiles are discussed. Domestic production incentives emerge. But silver resists all of this. You cannot build a silver mine overnight. You cannot force byproduct production to increase. You cannot recycle what has already been dispersed. By the time policy responds, the physical metal is already allocated. This lag is dangerous. It creates competition, not just between companies, but between nations. And competition changes behavior. Long-term contracts replace spot purchases. Supply chains become opaque. Pricing detaches from traditional benchmarks. This is when markets lose visibility. Traders see volatility but don't understand the cause. Analysts argue about macro factors while missing micro constraints. Commentators blame speculation, unaware that physical shortages are driving behavior. Silver has played this role before. During previous industrial transitions, silver demand surged quietly until supply could not keep up. When the market finally noticed, prices moved violently. But this time is different in one crucial way. Silver demand is now tied to the backbone of civilization. Electricity distribution is not optional. Transportation electrification is not reversible. Digital infrastructure is not negotiable. Silver is embedded into systems that societies cannot turn off. That makes demand sticky. Even during economic slowdowns, maintenance continues. Infrastructure upgrades proceed. Defense spending remains. Medical systems operate regardless of GDP. Silver demand does not collapse the way discretionary commodities do. This asymmetry matters. Supply is fragile. Demand is resilient. That is the textbook definition of structural risk. Tesla's 48-volt shift did not create this risk. It revealed it. The industry was already approaching electrical limits. Tesla simply crossed the threshold first. Others will follow because they must. And as they do, silver's role shifts from commodity to constraint. Constraints reshape markets. They force prioritization. They reward early access. They punish complacency. This is why the market reaction always comes late. Markets respond to price signals. Constraints operate before price moves. By the time silver prices reflect scarcity, manufacturers have already secured supply. Latecomers face shortages, not higher prices. This is when narratives change abruptly. Silver stops being discussed as an investment curiosity and starts being discussed as a strategic input. Headlines shift from charts to supply chains. Analysts scramble to revise models that assumed elasticity. But elasticity was never there. It was an illusion created by low demand growth. Now that growth has arrived, and it is arriving simultaneously from multiple directions: electric vehicles, renewable energy, grid modernization, defense systems, medical technology. Each layer adds pressure. Together, they create inevitability. Tesla's decision matters because it synchronized these forces. It accelerated adoption timelines. It validated higher voltage systems. It forced suppliers to commit. Once suppliers commit, demand locks in. This is why the phrase silver shock is not hyperbole. Shocks are not always explosive. Some are slow enough to ignore until they aren't. Silver's shock is measured in lead times, not headlines. And when the headlines finally appear, they will seem sudden, even though the process took years. That is how structural shortages always unfold. The future of transportation depends on electricity. The control of electricity depends on materials. And at higher voltages, one material stands alone. Silver does not ask for attention. It demands it.